Welcome. Today's notes worksheet is entitled Sets and Counting. This lesson represents for us an introduction to the next unit, and the primary objectives of the next unit will be to take a look at the number of ways or the number of possibilities for a certain set of events, or the probability or the chances that a certain set of events will occur. And much of that is going to revolve around the foundational piece that we developed today. So nice and straightforward, though, to start it out. So let's go ahead. We're going to probably put a few definitions into the mix here and do some examples as well. So let's start out with some definitions, some things that we'll see over the course of this unit. So first of all, let's go ahead and start with the set. So I have a set as a well-defined collection of distinct objects. That phrase will come up a lot during this unit. So distinct objects could really be anything: letters, numbers, actual something tangible. We'll go ahead and see that in action over the course of the unit. An element, well, the elements would be the objects of the set. So put that in there for me if you would. All right, so a certain set is made up of a variety of elements. A couple things. This one's just very particular here. We'll see what's called the empty set or the null set, and this would just be a set with no elements in it. Not too necessary for our purposes, but nonetheless it's in there. So a set with no elements. And then one other thing that will come up here, in fact this will probably be most of our lesson today dealing with it. It says if each element of set A is also an element of set B, then A is what is called a subset of B. So sets within sets, and that would be the case here. So let me just reread that, and then we'll go ahead and do example one to kind of back that up. But if each element of set A is also an element of set B, then A is considered a subset of B. So let's go ahead and just start out with example one here, just kind of writing a few things out. It says write all of the subsets of this set right here. So here's a set, just 3 elements in it, obviously the numbers 1, 2, and 3. And what we would do is write all of the possible subsets to that. So we're going to kind of start this out nice and easy, where I would create, and I'll try to draw brackets for you as best as possible, but something like that. I would try to create a set where all the elements in this set are in this set up here. So for example, something like this, the number 1, that would be a subset of this set right up here, because all of the elements here are in here. And you could maybe see them, maybe we can do a couple more. There's 2. So all of the elements in one set are in the elements of the other set. So this is a subset of this. All right, next one, how about 3? And so you can see in each case a 1-element subset of the 3 elements up above here. That would work out nicely. We could probably do 2-element subsets. How does that sound? So 1 and 2. That would be a subset of this right up here, of course. How about 1 and 3? That would be a subset of this right up here. And how about 2 and 3? That would also be a subset. So I'm hoping everyone at this point is starting to understand really the concept of a subset. We're going to add a couple more to this in just a sec. But essentially, all of the elements here are also in here. So this is a subset of this right up here. I could think of a couple others. One is very straightforward. How about this one? Obviously, the original set is a subset of itself because all the elements here are also in here, so that would be the case right here. And then this one seems a little weird, but it is considered the empty set also being a subset of this right up here. So that empty set with no elements in it is a subset of this right up here, because theoretically all of the elements in this are in this right here. So don't worry too much about this piece, but these certainly work nicely. All right, so that's just the first thing, just subsets within sets. We'll see a variety of relationships between sets, so that's just the first piece. All right, the next 2, which are going to come up a lot for us over the course of this unit. So we will see the words intersection and union. And just please make sure you understand the notation behind it. So I'm going to go ahead and box this up. These would be two sets, and this little notation right in here would represent the intersection of those two sets. And so here we go. When I talk about the intersection of two sets, I'm talking about a set consisting of elements that, and then here's going to be the key, belong to both A and B. So intersection has to be in both of them. In fact, we'll get a little bit of a visual representation of that in just a little while. But for right now, kind of write that definition in there for me. So in intersection, the elements have to be in both A and B. Now for union, it's a little different. Notice the notation, please. So differing notation here for union as opposed to intersection. And then let's start our definition out the same way. If everyone can do this with me, that would be great. So it's going to be the set consisting of elements that belong, and here's going to be the key, to either A or B or both. So it can be an A or B or both. We would take all of them in order to make up the union of those two sets. All right, so if that's not clicking for you, and by the way, let's underline a couple things here. So when I hear intersection, I think it has to be in both of them. When I hear union, I just think it can be in either or. So those are the buzzwords, I guess, that would go for intersection and union there. But again, if it's not clicking for you just yet, that's perfectly fine. Obviously, you can see on your paper, I have an example to kind of put this together here. So it looks like I have three sets just made up of a variety of numbers, very arbitrary in nature. But let's see if we can make heads or tails of the notation that you see on your paper for A, B, and C, and then how it relates to the two definitions that you've now put in place. So let's go. A looks like the odds, 1, 3, 5, 7, 9. B, just 1, 5, 6, 7. And then C, 1, 2, 4, 6, 8, and 9. Not too bad. And so let's go ahead and do letter A. In this case, what I'm looking for is the union of these two sets right here. And so union means basically I would take anything in A, so we would take all the elements in A, anything in C, so anything in C, and anything in both. So for example, you see the 1 is in both, so we would take the 1. I see the 2 is in C. I'm just going to try to go chronological here if possible, but it looks like the 2 would be part of it. I take anything in either A or C. I don't include an element twice, be clear on that. Obviously, when I have the 1, it's in both of them, but as an element, it is a distinct object, so I only include it once, as it is what it is. All right, so I have the 1, the 2, looks like the 3 over here. Looks like I have a 4 in C, so I take it. Again, I'm taking anything that I see in either A or C. I see a 5, I see a 6 in C, I see a 7 in A, I see an 8 in C, and I see a 9 in both of them. And so I would take them all. And so as you can see there, it would be the digits 1 through 9 as a result. So that would be the union of A and C. Okay, now, intersection for part B, I want the intersection of A and B and C. Now theoretically you can do this in two parts. You can do the intersection of A and B first, then take that and then do the intersection of C. But I think for our purposes here we could probably go ahead and just sort of do it all at once. So what is in both A and B and C has to be in all three for the intersection here. And so I kind of look at my numbers there. I see a 1 in all of them. Okay, so there's a 1. I'm going to take that. Let's see. It has to be in all three, everybody. So intersection, again, has to be in all of them for this to work. Let's see. I'm looking at a 5, by the way, in A and B, but not in C. So 5 is not an element that we would take in terms of the intersection here. Let's see if there are any others. No 6, because there's no 6 here. How about 7? I have a 7 in A and B, but not in C. So I'm seeing this, and again, you can confirm, refute, whatever you feel like here, but I think this is the intersection of those three sets right there. The only thing in all three is the element 1. Okay, good. Well, let's go ahead and do part C then, kind of a combination of the two, and you have parentheses in here. So why don't we do this? I'm going to take this in a couple steps. So first and foremost, I'm going to go ahead and find the intersection of A and C. That looks like this piece right here. Then I'm going to find the intersection of B and C. That'll be this piece right here in parentheses. And then after the fact, everyone, I think we'll go ahead and do a union and see if we can put that together. So I might do a little writing just below here. You are more than welcome to do that, or you can just start to see it and put it in your answer blank if you get a chance. So let's go intersection A and C. So these would be the elements in both A and C. Have to be in both of them. I see the 1. Okay, so the 1 is in both A and C. Not the 3, not the 5, not the 7, but it looks like the 9 is in both A and C. So in terms of the intersection of A and C, I'm getting a 1 and 9. So that would be this set right here. Again, excuse my poor excuse for a bracket, but that would be the case right there. All right, now there's my union. And guys, let's repeat. Let's do the intersection of B and C. So what elements are in both B and C? Well, let's see. I see the 1. The 1 is in both of them. So there's the 1 right there. Let's see. 5 is not. 6 is in both. All right, so I'm going to take the 6. And 7, nope. So everyone, I'm seeing just a 1 and 6. That's it. All right, so we have 2 intersections. I'm hoping everyone is in agreement on those. And now, guys, when I apply the union to those 2 sets right there, I take anything in those sets. So I take the 1, I take the 9, I take the 6, and those are the elements that make up my final set. So 1 and 6 and 9. All right, make sure that clicks for you. The primary context that we will see intersection and union will be in probability, and there's some really great problems that go into that. But we want to make sure we understand kind of the pieces right here. So intersection has to be in both, and union, we just take everything. It can be in either or. All right, good. So example 2, I'm hoping just that notation and the sets that I've created for you make pretty good sense. All right, let's go to our next set here. No pun intended. That was pretty bad. Okay, so let's see. I have the universal set, which we'll see just when we start to look at this a little more visually. So a universal set is the set consisting of all objects we wish to consider. So it's basically your starting point, essentially. Everything we want to consider is in the universal set. So a set consisting of all objects we wish to consider. All right, now from there, we're going to start talking about relationships of sets. And so the next piece, everyone, as you can see on your paper, is what's called the complement. So the complement of a set, and here's the notation we're going to use, with just a little horizontal segment right above the set notation. And so in this case, the complement is going to be a set unto itself. So it's the set consisting of all elements in the universal set so jot that in there for me, but not in set A. And again, if that doesn't click for you, that's perfectly fine. We'll see this momentarily with example 3. So let's see if we can start to put some more things together. That would be great. Let's go for letter A. So first of all, example 3, I have my universal set. That's what this is. And we'll just kind of do a 1 through 9 on those digits. It's just easy to use. And so these are all the elements that we wish to consider, the digits 1 through 9. And then if I define set A, it looks like as the odds, 1, 3, 5, 7, 9. Then the complement of that would be everything in here, but not in our set A. And so I'm hoping you would be in agreement with me that if set A consists of the odds, 1, 3, 5, 7, and 9, then it looks like the evens would be the complement. So 2, 4, and 6, and 8. And so that would be my set right there. I'm going to go ahead and throw some brackets around that. I don't know if I did that on the last one, but I'll go ahead and do that here. And so that would be the complement. Anything not in here, that's in our universal set. And again, there's some nice context for working with complements when we do probability, so keep that in mind. So the complement of A is anything not in here that's in our universal. Okay, and then actually I'd ask you to pause the video for just a moment. This would be interesting for you to see if you could pull this off. What would be the union of any set and its complement? And what would be the intersection of any set and its complement? So if you don't mind, pause the video for just a minute, and then come on back and let's see if you got them right. Okay, well, let's see how you did here. So union, and this would be a set A and the complement of set A. So I would take everything in A, and also I would take everything not in A, and you end up probably just getting the universal set. I'm going to go ahead and do that right there. So let's see if I can put this in for you. 1, 2, 3, 4, 5, 7, 8, and 9. So it looks like when we do the union, you end up just getting the universal set here. This would be all the elements in set A. This would be all the elements not. Include them all, and you've got the universal. Whereas when we find the intersection of a set and its complement, well, there is nothing that overlaps between the two sets, and so as a result, for this one, hope everyone saw, you end up getting the empty set. So the intersection between any set and its complement will always be the empty set. Nice. So again, just set theory, so to speak, for these, but some interesting ideas and concepts that we're developing. All right. I'm going to move on to my next board here, and I will take a look at what are called the Venn diagrams. So these Venn diagrams will allow us to go ahead and basically represent these visually. So in reality, we're going to draw pictures here. And so what I'm going to do is just kind of give you a quick definition, and then as you're going to see, there's an investigation just below to kind of do some other buzzwords that kind of go with this, and we'll see this nicely with the visual diagram here. So a Venn diagram, it's just representing sets as circles enclosed in a rectangle. So maybe you've seen these before, and if so, that's great. Kind of allows us to kind of work on some counting ideas in just a few minutes, but let me just make sure I have this right for you. Representing sets as circles enclosed in a rectangle, which represents, in that rectangle, will be our universal set. So the rectangle, here we go, represents the universal set. Okay, good. And so we'll go ahead and draw some of these out here, see what you think. Get some ideas going with what is called a proper subset, disjoint sets, intersection again, union, and then complements as well. So we're going to do a little shading in here momentarily. But everyone, why don't we start this out? It looks like I have for this investigation 1, 2, 3, 4, 5 that we're going to be taking a look at. Right away, everyone, if you can maybe get me 5 rectangles there, something like this. Let's get that taken care of first. And then maybe something down here. And for me, one more right in here. All right, and then let's see, this will be the proper subset. Just want to label these appropriately for you. So a proper subset, disjoint set, the intersection of two sets, and then the union of two sets, and complements. All right. And in each case, everybody, really, again, the rectangle represents our universal set. So if you don't mind, I'm going to shorthand this. I'm just going to put U set right up here. Hopefully, if you can do this a little better than I'm doing it, you might want to actually write universal set up there. I just got a little lazy and it's just a little tough to fill in such long words in these little rectangles. But if you get an opportunity to go ahead and do that, this would be the universal set in each case. And then what we're going to do is kind of talk about sets from that. All right, so when we talk about proper subset, basically what we're going to do here is start out with a set A. We're going to call that A right in here. So everyone give me a big circle there to represent all of the elements in set A. Now, if set B is a proper subset of set A, very simply, all of the elements in B are also in A. So I'm going to go ahead and put a B right in there. And then if you get a chance, it's tough for me to do this with this board, but what you're going to do is shade that. So this would be set B, and this would be a proper subset of set A. All the elements here, as you can see, are perfectly in set A as well. So B is a proper subset of A. That's how we would phrase that one. So again, just try to shade as best as possible there. Put a big dark B in that circle, and then just lightly shade that circle. It's just hard for me to do that up on the board, so you'll have to use your imagination a little bit with this. Okay, everyone, two disjoint sets. So here's set A right over here. If they are disjoint, very simply, there is no overlap between the two. So there's set A, and there is set B. And as I said, there is no overlap between the two sets, so they are considered disjoint. One good question about the disjoint sets would come up before doing the intersection over here. And as a matter of fact, here's what I would ask you with these. What would be the intersection of these two sets right here? And if you look at these, you can see that the intersection, just from a visual perspective, the intersection would be the empty set. So I don't know if you want to write that below or not. That's totally your call. But the intersection of A and B would be the empty set. Okay, that's what it means to be disjoint. All right, next one, everybody, would be intersection. And so let's go ahead and put this together here. Here's A, everybody. Here's B. And so remember, the intersection would be all the elements that are in both sets. And what that would look like visually is the overlap. And so as a result, if you get an opportunity in there, this would be the intersection of A and B. The overlap, of course. All right, very good. Has to be in both A and B. Now, I like that piece because then we can contrast that with union. So if you get an opportunity here, let's go ahead and maybe draw the same two. And again, this is really hard for me to do. I'm going to put a big A in here and a big B in here. But if I'm looking for the union of those two sets, then very simply I take anything in A, anything in B, or anything in both. I take all of the elements possible. So if you get an opportunity, just very, very lightly shade really everything in those circles. There we go. I take everything in A or B or the intersection of the two. Okay, good. So you can see kind of the difference right away visually between intersection and union. And then what do you say we do the complement here? So here everybody would be set A. And what we talked about in terms of a complement would be everything that is not in set A that's in the universal set. So what would that look like in terms of shading? And again, you'd probably do this better than I can out here, but essentially it's everything out here. That would be the complement. And again, just hope that makes pretty good sense just from a visual perspective. All right, feel free to take a look at your text as well there. They could probably do a better job at least drawing these than I can, but I'm hoping at least kind of the phrasing works out nicely for you for these five, especially these last three. That's the key, the intersection, the union, and the complement. All right, well, let's go ahead and take a look at sort of the last piece, do an example, and then kind of put a couple things together with this. So we're going to use a little Venn diagram here to relate these, and let's answer the question. So it says, in a survey of 100 students, there are 57 students in pre-calculus, there are 26 students in statistics, and 12 in both courses. So how many are in pre-calc or statistics? Interesting. All right, so we have to be a little careful with this And I'm going to kind of show you how we're going to play this out before doing what's called our counting formula. But everyone, if you get an opportunity, let's go ahead and make a nice Venn diagram here. Everyone give me a rectangle on your paper if you would. And it looks like our universal set would be the 100 students. So I'm going to just kind of put a 100 up there. So that is our universal set of 100 students. Now I have some students in pre-calc. And here's where we're going to have to be a little careful. I have some students in statistics. And I have some students in both. All right, and it says how many are in pre-calc or statistics. It looks like we would just take 57, add that to the 26, and then add that to the 12, and that would be how many are in pre-calc or statistics. Unfortunately, that's actually not how it works. And so let's look at it visually, and then we will apply it to what is called the counting formula here to kind of see it in action. So let's start out with this nice visual diagram, and let's start with the fact that these are my pre-calc students, these are my statistics students, and there are 12 that are taking both. So everyone, if you would, the intersection would be 12. So everyone put a 12 right in there for me. Now here's where the numbers are in fact a little misleading. It says that there are 57 students in pre-calculus. Everyone see that right up there, 57 in pre-calculus. Meaning in this entire circle, there would be 57 students. But here's the thing. 12 of those students are in statistics as well, right? They're part of the overlap that I just created right here. They, of course, are still in that big pre-calculus circle. So the question then becomes, how many students are just in pre-calculus? Because this includes the students who are in stat also. This includes the both. So I'm hoping you guys all see that this is actually, if I just asked you how many students are just taking pre-calc, it seems to be that there would be 45 students just taking pre-calc. Because the 45 and the 12 make up the 57 students in the pre-calculus circle. So it's easy to kind of jump the gun on this, put a 12 here and put a 57 here. But notice, that's why the visual Venn diagram is so good, because you see that would be incorrect. I don't want to include people twice. That's the key. And so now, look at that circle, everybody. I have 57 students in that circle. 45 just taking pre-calc, and 12 taking the other class also. All right, now let's go to the next piece. Let's go to my stat circle over here. It would be very tempting to just say, okay, 26 students in stat and put a 26 right in here. But remember, out of those 26 students, 12 of them are taking the other class. So the question then becomes not how many are in statistics, but how many are just in statistics. And the answer, of course, has to be 14. Because then I have my 14 and 12, which makes up the number that I was given in the problem. There are 26 students in stat, but 12 of those students are also taking the other class. Now I think we've got it. It says how many are in either pre-calc or stat. Basically, what's the union of those two events? And in this case, as you can see, I've got 45 here, I have 12 here, and I have 14 here. And if I add those together, let's go ahead and do that together. 45 plus the 12 and plus the 14, I get 71. By the way, which means in terms of the complement, it looks like the complement, which would be out here, would be 29, because I had 100 total. So if I asked you how many are in neither course, it looks like 29 students. But that's great. I'm hoping everyone is comfortable with that Venn diagram, starting with that inside, and really interpreting this number and this number right here. That's the key. Okay, now if I gave you this problem, would you always have to do a Venn diagram? Not necessarily. And we're going to see this come up when we do probability, so that's kind of the reason I'm really putting this in place here as well. It's not too big of a deal here, but there's some great probability problems that we're going to do with it. So here's the idea. It's all based on finding the union, which we basically found up here. So this n just means the number. So the number in a union of two sets is actually defined by the following formula. And it's basically this. the number in set A plus the number in set B minus the number in the intersection of the two. And I'll show you kind of why and how that works momentarily, but for right now, if you don't mind, kind of jot that in, and that's going to be the key. So if I asked you, and we're going to revisit example 4 momentarily using this counting formula, but basically if I asked you for the union of two events to occur, we take the number in A, add it to the number in B, but the problem here is, everybody, we don't want to include elements twice. And in order not to include elements twice, we have to subtract away the intersection. Okay? Well, let's go ahead and try this out, and maybe we could see, again, how that formula relates nicely to the example 4. So example 5, use the counting formula to answer example 4. So here's what it would look like, everyone. I would be looking for the number in pre-calc or stat, right, which is the union of the two. And so what we would officially do here is take the number in pre-calc, add it to the number of people in stat, but here is the key, everybody. We don't want to include people twice. If we include people twice, we mess up our number. It becomes incorrect, basically. And so what we want to do here is subtract the intersection away. So sorry about that. Let's see, number of pre-calc and the intersection of stat. All right. Well, let's go ahead and do it. Watch what happens here. So everyone, if you would, the number in pre-calc would be 57. The number in stat was 26. And here's the problem. There were 12 people that I included in here, and I also included here, right? So if you remember correctly, there were 12 people in both courses. Those 12 people are included in this number, and they're also included in this number. I don't want to include people twice. So in order to include them only once, I have to subtract away the intersection. Now I can just use these numbers right here. And by the way, if you take 57 plus 26 and subtract away the 12, guess what you get? 71. So I like this. I love the visual perspective. That Venn diagram to me works so beautifully. And it really starts to clarify the idea of not including people twice. And in terms of just using the numbers that were given in the problem, this allows us to do that. So I take the number in set A and the number of set B and add them together, but I don't want to include people twice, so I subtract away the intersection. Now I've included those 12 people only once, only in one of these numbers as opposed to both. Cool. Let's see, there's just one last piece and then we'll wrap this up. It says use the counting formula to answer the following question. What would occur if the two sets, A and B, have no elements in common? Then, well, very simply, there'd be the intersection would be 0. And so we would just do this. So the number in the union would just be the number in A plus the number in B. Okay, so, and again, this would only be if the intersection is equal to 0. So if you don't have any overlap, then again, what we're doing is just adding the two together. And we'll see this a lot in probability. Using the word or typically translates into addition. We will definitely see that piece. Okay, well, some interesting stuff there. If something doesn't click for you, please feel free to use your textbook on this. It's a very kind of straightforward section in that it's really just definitions, terms, and then examples. So please, read over your textbook section if you need to. I think that would help in this case. And then also try some examples on your own, just making sure it's all clicking. Don't overthink this too much. I think there's plenty of things out there that is more important for our purposes. But it's a good start nonetheless. Anyway, of course, thanks for listening. If you have questions, don't hesitate to ask.